Welcome back, ladies and gentlemen, to the Actuarial Academy. This is Dr. Me, and we are going to look at a problem involving an electrical system that fails if both subcomponents of the device fail, where the lifetimes of each of the subcomponents is modeled as a random variable, respectively T1 and T2, and they're independently distributed with density f of t equaling e to the negative t. You should immediately recognize that this is an exponential random variable with lambda equal 1. And now the cost is actually what we're interested in operating the device until it actually fails. And this is given by this transformation, where the cost is actually equal to twice the lifetime of the first component plus the lifetime of the second component. And so we want to actually find the density function of z. So this is a transformation problem, and it's a little bit more involved because it involves addition, the sum of two independent random variables. So when you see that, you should immediately recognize, oh, this is probably some form of a convolution problem, which it indeed is. Okay, the only trick here is that we're not just adding up two independent and identically distributed random variables, we're actually transforming this one first before we make the addition. So we're going to first have to figure out what the density of this is, and then use its density and to model this piece, and then of course we're already given the density of this, and then use the convolution formula to figure out the density of z. So that's a nice segue into our fact. This is a fact that you should memorize before taking the actuarial test. It's fairly easy to memorize. It's pretty intuitive, and it is the convolution of f of x and f of y. So if you have two densities, fx and f of y, and you're interested in the sum of the random variables x plus y, then their density is actually given by this formula here. So since we are trying to find the density and we're evaluating at z, we're trying to find all possible combinations of x and y that give us z. And that's done through a convolution. So we evaluate that very simply by f of x, we model this, and we evaluate z minus y. So we actually take out y from here, and f of x is the likelihood it takes on that value. But then we need to multiply it times the likelihood that f of y actually takes on the value y, because you see these arguments here actually sum up to z. And then we do that for all possible values of y. So that's the convolution, and that's kind of a nice intuitive explanation of how this convolution actually works. So let me just reproduce what we're trying to do here. So we have z is equal to 2t1 plus t2. I will let you do some research to convince yourself. I actually have a video out posted that the density function of 2t1 is equal to 1/2 e to the negative t over 2. Okay, so that's a little exercise in itself to actually solve that. And we already know what f of t2 is. Evaluate at t. These are just dummy variables, by the way. We could put x, y, or z, whatever variable we want in there. And this is, of course, already given to us as e to the negative t. So these are now the density functions of 2t1 and t2 respectively. So these are going to model, or are going to mimic, f of x will be this piece, and then f of y will be this piece. Okay, and then we'll just apply our convolution formula to find the density of z. And this is where we just apply the formula. F of z, evaluate at z, okay, is going to equal to the integral. We will worry about the limits of integration here in a moment. Of our density involving 2t1, again, that's going to analogous to our f of x here, but we're going to evaluate it at z minus y, so this will be 1/2 e to the negative z minus y over 2, and then times our density involving t2, again, that models our f of y here. So this is e to the negative t. E to the negative y, because we're evaluating dy, like that. Okay. So we need to understand what our limits on y are. So y is the random variable which can only be positive, or at least non-negative. So the lowest it can go is 0. Now the highest it can actually go in here is z. Okay, and we can see that very clearly here. Y cannot be larger than z, otherwise this is negative. And the density is not defined for a negative random variable. So the largest it can go is z. So convince yourself of that. It's a little tricky to understand that piece, but once you see why that's the case, it's not true for all densities. Like for the normal, you could have it go negative, but here y cannot go larger than z. So that's actually the correct statement or representation of f of z, and now it becomes a calculus problem. So let's work this out. This then would just be equal to, and you can pull out a constant here, 1/2 e to the negative z over 2. And then once we have this out front, we still have a positive y divided by 2. And then you're subtracting the y, so you're left with the integral. So I'm going to kind of go quickly over the algebra, let you convince yourself of that. This will be just negative y over 2 dy, which is equal to, and we could do the calculus or the arithmetic or the algebra here, but I will let you work on that piece. I will just kind of write out some intermediate step and then the final answer, then plus 1. The final answer is actually equal to e to the negative z divided by 2 minus e to the negative z. Okay, and that's our actual density. Well, just to be complete, we'll say z has to be greater than or even equal to 0. That's fine. And that's actually our density of the cost to operate this device until failure. Thank you.